Well, it's my great pleasure to introduce the next speaker, Jay Alammar. Jay is co-author of the Hands-on Large Language Models book. I'm sure many of you have read, seen, or heard about it at least. It's published by O'Reilly. He's also the Director and Engineering Fellow at Cohere. That's a pioneering provider of large language models as an API. Through his popular AI ML blog, Jay has helped millions of researchers and engineers visually understand machine learning tools and concepts, from the illustrated transformers, BERT, DeepSeek, and otherwise, including yours truly. You know, when there was like barrage of terms being thrown at back in the day, you know, going from land chain, chain of thought, train of thought, tree of thought, whatever it was. I was like, what the heck is going on? And I would go back to the last refuge and look at what Jay was talking about to at least get a sense out of it. And without further ado, please welcome Jay.
Thank you so much. That's a great intro. Truly appreciate it. Yeah, it's an honor and pleasure to be here. I've fed on KDD papers for a decade or more. There's so much interesting stuff. Truly honored to be here with you and sharing with you something I've been fascinated with for nearly a decade. So as I mentioned, the illustrated transformer is the article that I wrote that people might have come across. At the time, we had no idea that the transformer would make this much of a big jump. At the time of writing, there were two major attention mechanisms in deep learning, and then there was this new third one, but it kept getting more important over time. So now the article is around 7 million page views, which is I find ridiculous. But I've been wrapping my head around the field and working at Cohere, which is a large language model company. It's one of the earliest ones working in this space. I'm here to share with you a bit of the things that we learn inside a factory that creates and pre-trains LLMs. A lot of this is in the book, Hands-on Large Language Models. Right after the session, we'll be doing a book signing at the table at the back there. We have only like 15 copies that we'll give out for free. So the first 15 or 20 people who line up near that table will get copies. The good thing that it is in the room. 19 copies. So this is not a new slide. I've been using this slide for 5 years now, and it keeps getting more and more relevant. So every 10 or 15 years now, we see a jump in computing technologies. So the personal computer offered many changes, many economic changes, many economic giants that come. And then 10 or 15 years later, we have the internet and then web browsers, and that's how companies like Amazon happen, and Google. While in the personal computer age, that's how Apple come to being, and Microsoft and HP, and a lot of these companies. 10, 15 years later, we see mobile apps, and then that also creates a ton of new opportunities, new kinds of jobs, new business models that were not possible in the past. So that changes the landscape of the world. And with large language models, we say that this is most likely, this is definitely one of these. But I also go back in time and say, big jumps in language technology have a way of shifting the human species. So when we first invented writing, that's literally what we call the beginning of history. That is the definition. The beginning of history is when we invented this way of preserving thought and knowledge and information in records. And that changes us as a species. 500 years ago or so, the printing press came around. Before that, if you needed a copy of a book, you needed to go copy it by hand. It was very expensive. Most people were illiterate. This gets invented, and then in 400, 500 years, we are where we are now. We're shooting Teslas into space and doing wild things. So will the rise of AI and deep learning and LLMs take us to a next one? It's looking more and more likely that it's going to be as transformational as these. I put the chances at 20% when I was presenting this 3 years ago, but that number keeps getting up to a lot of people. There are multiple points where we can point at where this starts, but one good point, one arbitrary point, in addition to the transformer, which we'll talk about, is when prompt engineering came together. So this is the T5 paper from 2020, where it was one of the first attempts at saying, okay, we can formulate lots of problems as text shaped in this type of prompt. It's not yet natural language, but this is just 1 or 2 years before sort of the thought of the language model as a general purpose problem-solving method starts to happen. This is a plot. I tend to plot things with Matplotlib, generally in maybe Jupyter notebooks, but I did not plot this plot. I just had a link to a data set that's on GitHub. And I'm using an agent here, so this is an agent from a company called Manus. I just gave it the URL and said, give me a plot of this data. And then here you see everything that is happening on the screen, the agent is doing. So an LLM is operating here and has a problem statement of give me a plot of this data. And then it's using tools. And on the right here, you can see the computer tool that it's using. So it has its own virtual machine with a browser. So you see it sort of trying to say, okay, how can I access this? How can I read this data? It also has access to another tool, which is a bash or a command line. So it can issue these commands like, you see writing CD, look at these files. You see it's reasoning. You can see the reasoning and the multiple steps that it's doing on the left. And it's going about this problem. Now it's generating text, so the language model is generating code. Not only is it generating the code, it also has a tool to execute that generated code and then operate on the output of that and then solve problems over steps, over tens of steps, maybe 50 steps. And then here you have a first version of the plot. The model is looking at it and is saying, maybe if I had a trend line, this plot would be better, because this is a multimodal model. That's how it's sort of able to view this. So it's not happy with this. So it goes back and creates another version with the trend line. And then it writes an MD file sort of saying, these are the data sources, these are some of the major statistics of this plot. And this is sort of where we are. And this is quite surprising. So I jumped into language models, doing full-time, had it as my main focus for about 5 years now, around GPT-2 and GPT-3. Because that was the first, GPT-2 was the first time we had a software system that was able to write an article that you couldn't tell, did a human write this or did a software write this? You have to cherry pick very hard to sort of find that one, but it was just beginning to be possible. Within 5 years, now we're seeing things that we never thought software would be able to do. And understanding the implications of what this is something that all of us sort of are wrapping our heads around. And so here in the top, today I'll be happy to sort of share with you some of the main intuitions of how these models are trained, how they work under the hood, how to sort of think about them. These are going to be very highly accessible and visual intuitions that help you sort of dig deeper into any areas that you want to dig deeper into later. So this is where we are now, where the transformer was in 2017, prompt engineering with the T5 model around 2020, and here we are now. So a lot of what we'll cover is just this period. The training has not changed very much. So how do you train a modern, current generation era large language models? So you start with randomly initialized model of a certain size, and you do language modeling. This is where they get their name. Predict the next word, and then you end up with a base model. And this is what GPT-3 was, if you have a sense of using it. Those models, the base models, are around. They're an important part of the recipe, but they're very hard to use and to prompt. If you give it a question, it might give you a list of other questions. Your prompts had to be very detailed and in specific sort of formats to be able to work appropriately. So the next thing to improve those behaviors is to do what's called supervised fine-tuning, or instruction fine-tuning. And the concept here is that if I give you a question, I want you to give me an answer. If I give you a command, if I tell you to write an article about dolphins, here's the kind of article that I want you to write. And so that's a way of maybe improving the user experience. And then up until about 2 years ago, the third step used to be called RLHF, reinforcement learning from human feedback, which is a little bit more polishing for the output, the type of outputs that you want out of the model. Maybe you want shorter or longer outputs. Maybe you wanted to avoid talking about certain topics. Last year, this has changed. It's still reinforcement learning, but reinforcement learning is back, and it's not just RLHF, and it's unlocking lots of capabilities with reasoning models, for example, that we'll talk about here. Two important terms are what pre-training is and what post-training is. There's no longer any training. There's only pre and post. So pre-training, that's your language model, language modeling. Post-training needs less data. So here you can get around with tens or hundreds of thousands of data points. While in pre-training here, the Quen 3 model was, pre-training data set was about 37 trillion tokens or so. So you need ridiculous amounts to have a really strong base models, and that enables you to sort of pool the capabilities of it in the next training phases. The instructions you can see for instruction tuning are kind of like examples like this, where you have a question and an answer, or a direction and sort of a way that you want the model to sort of format the output. So human preference for outputs is important. You might have a sense of that. But one way to collect this data is to give a model a prompt, get 2 generations out of it, and then ask a human annotator, which one do you prefer, which one is better, and then you get that sort of rating. And from that you get, let's say, a value judgment that can be either a preference of one A or B, or it can be a score for the quality of generation A is this number. And this was a sort of a breaking point. We needed a new toolbox of tools to be able to back propagate and update the model layer by this external system, which can be a human. So if it's a human that's labeling these, you cannot back propagate and update the weights based on that. So the book of, or the toolbox of reinforcement learning is where we got these tools that enable us to update the model based on a score created by a system that could be a human, or it could be automated. So the way that it's automated is by us creating what's called a reward model. And a reward model can take many shapes, but one of the more common ones when these started out is it's a classifier. And you take the same language model, you remove the neural network at the very top, which was just used to predict the next token, and you add a classification. So that becomes your quality classifier. And you train it on preference data from human annotators. And then from that, you can have a model that is able to give you these value judgments. Is this a good completion for this prompt or not? And that is very important part of the puzzle to create lots of, say, huge amounts of this data that you need to create a high quality and high performance language model. This is the kind of data that these models, these reward models, are trained on. So the first one is, it's an example with, you have the same prompt, and then you have a preferred generation and a rejected generation. They can both be good. It does not necessarily that one is good and one is bad. They can both be good, but one is always better than the other one. And that continues to give the model the signals. And this is a thing we'll see with things like GRPO when we talk about them in a minute. So this is the training objective. Basically, when you're training the model, you say, okay, I know this one is preferred and this one is rejected. I just need you to assign a score for the preferred one that is higher than the one for the rejected score. And this is sort of how the Alammar 2 DPO method sort of works. That's the exact formula from there. That's what the two numbers sort of mean in that formula. So that's the training objective of creating a reward model. And that is one of the major pieces of how we can get the models that we have today. And then from that, you have a trained model that's able to assign a score, a quality score to any input prompt and generation that you have. Now the big thing is, and the big thing maybe since November of last year, is this reasoning. And this really pushed the capabilities of these models to areas where even people in the field didn't think were possible yet. So that's been sort of fascinating. And one area where this is most demonstrated is the DeepSeek R1 model. I was in NeurIPS last year. NeurIPS came in this period where OpenAI's O1 reasoning model was released, but nobody had any idea how it was trained. And so every conversation in the NeurIPS conference was, what are the best ways to sort of train models like this? And then only, let's say, a couple of weeks after that, DeepSeek releases the R1 with their recipe, and the model has these same capabilities. So we can talk a little bit about what's the intuition of how we were able to create, and how the industry is now being able to create these reasoning models that output in, let's say, 2 steps. They output a start thinking token, and then they start thinking for a while. It's going to be a short or long time, or long number of tokens. And then once they've sort of concluded thinking, they say, okay, here's the real answer. And so it's a 2-step process, but that enables them to solve problems that they had no possibility of solving previously. These models are trained in the same formula that we saw. So we saw base training, supervised fine-tuning, then reinforcement learning. This is the same thing. We're just not showing the first model that's untrained. So DeepSeek R1 started out with the DeepSeek V3 base model. So that's a model that they released earlier. And then was SFT'd or supervised fine-tuned in a specific way, we'll talk a little bit about. And then there's a large-scale reinforcement learning step that happens behind that. And that's a part of the training that's growing very quickly this last year. So lots more of the compute is now going through to these massive reinforcement learning steps. So they're able to create this model by doing these 2. If you think through the supervised fine-tuning, there are 2 categories for the data that went into training this. The first one is just general SFT data. You can find lots of open source supervised fine-tuning data. But then there are these long chains of thought examples. This is the reasoning data. Those were rare, and those were very hard to sort of label, and you needed so many of them. So for DeepSeek R1, they were able to get 800,000 of these. And that is the secret sort of sauce that it took the open science community sort of some time to replicate. One of the best parts of reading the DeepSeek R1 paper is to see how did they come up with those reasoning traces. And to do that, they have, let's say they do a couple of methods. So about 5,000, I think, of them are labeled by humans, because these are very expensive. You need these long traces. But they've trained a different model that is very good at reasoning data. They call it in the paper DeepSeek R10, and that is the one that sort of created the vast majority of these. And so here you have kind of a recursive problem. So okay, to train this one, you need to train this previous one, but it was easier to create this first one just by doing reinforcement learning directly. And this was the second maybe more surprising thing about the DeepSeek R1 model, is that you're able to create a model just from getting a base model and doing a lot of reinforcement learning on it without SFT, and then have something that actually does really, really well on reasoning problems. And so you can think of the RL steps are like these, so you can think of each of these as steps. And that's the process to create R10 that then is used to create generate the training data. They did not release R10 because it wasn't doing well on non-reasoning problems. It's not a good it's a good general model, but it was really good for these reasoning problems. And from that capability, it was possible to use it and the data that it generates to create a better model that does reasoning, but also does everything else that people expect from a model. You can think about the training process as kind of like this. So these are all reasoning problems, so they are either either math problems where you have the problem and you have the gold answer and you can compare directly. That's the majority of the class. And then you have code problems where you have let's say, think of lead code problems, for example. So you have the request or the question, and then you have unit tests to verify, is this answer correct or not? So this was the major shift, that we have this class of problems that are difficult, but they're very easy to verify automatically. So what happens in each training step? So we can take an example. So the training prompt here is part of our training data, is this request to say, write Python code that takes a list of numbers and return them in sorted order, for example. Just think of a lead code, competitive coding problem. And so you have a previous, let's say the checkpoint that you're currently training of the model, and say generate 4 different answers for this. And you increase the temperature a little bit so you get a little bit of variety in the answers that the model generates. And then you have, it will generate these 4 answers or 8 answers, and then you can go and verify them. Are these correct? Are they not? Are they good? What's the level of quality between them? So let's say the first generation, it says, here's a joke about frogs. That's clearly not the answer. That's not the code that we're looking for. Then the second one outputs bash or command line code. That is not Python, for example. So we can verify each of these automatically. We have automatic verifiers to train all of these. And then the third one is Python code, but it doesn't really do all of what we asked it to. It doesn't pass all the unit tests that we had for this problem. And then the last one is Python, and it passes all the unit tests. And then now we have a value judgment. This is wrong, this is wrong, this is slightly less wrong, and this is correct. And so from these value judgments, we can get this training signal that you get exactly by just applying something like the GRPO algorithm, which this is a step of the group. In GRPO is this group of 4 examples. So you're extracting signal from these multiple generations. And so you use these scores to update the model. So the next time it's attempting to solve a problem, the solutions look less like the wrong answers and more like the correct answer. And so you do this across very, very long training cycles, tens or hundreds of steps, and the quality of the model keep increasing. And that's how you get these capabilities for reasoning, but also for code generation. And this gives you a little bit of a sense of how this is trained. But then when we look at the example that we saw, there are multiple steps that the model was doing. Let's say this behavior of calling tools. This is another concept that the model, if the model is to do better in becoming an agentic model that is able to call tools and solve problems over multiple steps, it needs to see that in the training data, or maybe supervised, fine-tuned on it. And so that's a little bit of what happens here. So you have training data of the LLM, and you say, okay, you have these 3 tools that you can use. You can use a Python interpreter, or a web browser, or the command line, or bash, and it solves the problem. It calls the right tool and writes the right code to do that for each step. And with that, let's say this is a visual kind of representation for what was happening in these steps that we saw the model take before it was able to generate this plot. And then this is what we call a trajectory. So if you haven't sort of worked with reinforcement learning, that's one of the terms that are now important for language models, these agentic trajectories. So now your outputs are not just a single output, they're multi-step of tool calling and then tool parameters, which can be code, which can be function call parameters. So looking at trajectories is that's one term. Another term is this rollout. So in the example that we saw of 4 examples, those were, let's say, immediate generations. The model, we give it a code problem and it outputs the code. But if you want to train an agentic model, you will do these rollouts where the model has access to the tools in the training phase. And so that's where you sort of create these rollouts and you grade them and you evaluate them and you extract the right training signal from them. A lot of the basics of this entire science are in Sutton's book. who just won the Turing Award for it last year. And so here you find two major areas where reinforcement learning is now very important for large language models. So one is to create that interim reasoning model, to create these long chains of reasoning data, and then to make the model work for general purpose use cases, you also do another very long step of reinforcement learning after the supervised fine-tuning. Now, we talked about reasoning prompts and how we have these rule-based verifiers. We saw the unit test, for example. We saw comparing against for math. We saw comparing against the gold answer. So for reasoning prompts, we have these rule verifiers, and that's where you get the term reinforcement learning with verifiable rewards, because now you have these verifiers. And whatever model behavior you're after, as soon as you're able to define a static verifier that's able to judge, is this the correct output that you're after or not, then you've gained on the problem very much, because you can replicate this recipe. But then not everything can be verified automatically, unfortunately. So if you're writing poetry, it's very hard to do that. So you still need these reward models for general prompts, writing requests, question answering, translation. For all of these cases, you still have these multiple reward models, and they often tend to sort of be focused on specific capabilities, either helpfulness or safety or other areas that you sort of want the model to improve on. You will see lots of talks about recipes. So we talked about the general recipe for how these models are created with those 4 boxes. This is the recipe for creating the Quen 3 model. And it follows sort of similar steps. So you have your base model, and then you train on the long chain of thought, sort of cold start, and then you do the reasoning. And then they add these additional steps. So you end up creating a massive model. That's the 235 billion parameter. That's a giant model, and then they distill it into these much smaller models that are much more capable, let's say, of models of the same size at the time of release. So this is a recipe to go through, training a big model and then distilling it to smaller models and enabling them. One of the biggest shifts, and I don't see this sort of being talked about, and it's implicit in a lot of what we've talked about, is that we wouldn't have gotten here without massive jumps in the ability to create synthetic data. So synthetic data, you often hear about, okay, the internet is becoming polluted with so much LLM-generated garbage and listicles and blog spam, and that is correct. And training models on that bad synthetic data is bad, and that does, let's say, reduce the quality of these models. But you can only have the performance and the capability of the current models by having high-quality synthetic data that is created with very careful recipes that injects diversity, that inject that really utilize the capability of the most recent models. And you can see that these models they keep lifting up other models. So if you couldn't have had DeepSeek v3 without DeepSeek Cohere, which was DeepSeek 2.5. Because we talked about when we were talking about the code problems, we said we have problems and then you have the unit tests. Those unit tests tend to be generated by another LLM. And so these LLMs keep pulling you up, and they keep you can build up on the previous generation. It enables you to build better and better models. And so getting more dexterity in creating synthetic data is very important, and I don't feel it's sort of recognized enough. And it works sort of in both. You're seeing it in the pre-training, so massive amounts of the pre-training is now synthetically generated, but also you see it in SFT. What the big jump here that sort of made me realize this is that Llama 2, the post-training data, was all human annotated. Llama 3, the post-training data, was mostly annotated by Llama 2. So you can see the jump between these two papers. I just sort of read them. There's still some human annotation that's, you don't get rid of it completely, but now you have an incredible additional source for data. And then, just on this point, whatever happens in RL, that is also synthetic data, right? You have the 4 generated answers, these are synthetic, and you have ways to sort of evaluate these as you go. So one thing that we sort of worked on at Cohere is we released this model, Command A, and we have a very detailed tech report that goes into it. But one of the ideas that was very useful for us is this idea of model merging, is that you can have 2 models that each is capable in a specific capability. So this model, for example, is really good at coding, and this model is really good at retrieval augmented generation. And then you can merge them, and you have one model with the same number of parameters, but that improves on both capabilities. So here you see model 1 is really strong at capability number 1, but not mid at number 2. The other one is very good at capability 2. If you merge them, you can sort of get models that are of high scores in both. Approximating, not necessarily reaching the specific expert. And that works as simply as you have all the weights here, all the weights here. You average across all of the weights of the networks, and then that's your merged model. And there are other slightly more advanced ways of merging the models. And so that's how you understand our training recipe that we write in the tech report. So here you start with the instruction tuned model, and then we created 7 specialist models. And there's an organizational aspect of this, is that you can have individual teams working on these individual capabilities. So you have your RAG, retrieval augmented generation, and agents experts. So you can have a team working on that model and data specifically. And then multilingual, code, math and reasoning, long context, safety, and instruction following. And then you end up with these 7 models, and then you can tweak the weights. You can have a weighted merging of what capabilities you want most out of this. And then you have a merged supervised fine-tuning checkpoint, and then you use RL to train the RL versions of all of them, then you merge them back, and that's how you sort of come up with this. We write all of this in this massive tech report. It's 40 pages with all of these details for every model. We're really excited to be able to sort of share this with the community. So, a high-level overview of the model. So we talked about the training process. We can touch on the model with any level of details. But one of the more, let's say, high-level concepts that are involved here is that we know that models take text, but before the model chews on the text, it needs to be broken down into tokens using a tokenizer. So that is the first part of the model. And then these tokens need to be represented as vectors, that the model is able to operate on them numerically. So language models are language calculators. They have never really seen any words. They see just these tokens, and they see them in these sequences, and that's how they extract the meaning. And here you can see one way of breaking down tokens. And so this is an example. So you break them down using the tokenizer, you assign the token IDs, and that's what you give to the language model. And then it outputs a token ID, or it outputs a vector that can be mapped into a token ID. To get a good sense of the tokenizers, you can take this piece of text and pass it through multiple models and see how each tokenizer sort of tokenizes it. We just heard talk of BERT. We can see the BERT tokenizer at the top, and we can see, let's say, GPT-4 at the bottom. You can see some information gets lost here. So the earlier, let's say, BERT models, you lose, let's say, new lines. And so if there's information, if that's a conversation, there's information encoded by new lines, that is lost. You can see emoji is lost, multilingual is lost. The Chinese character and the emoji are both unknown tokens in BERT, for example. And so there's, especially for multilinguality, there are important aspects in tokenizers. To understand the transformer, to have a sense of the transformer large language model, the first intuition is to understand that it generates tokens one by one. Even though we see the final text all at once, it's actually generated one by one, and then that goes through these 3 major components, where you have the tokenizer, the stack of transformer blocks, and the language modeling head. And the process goes through them sequentially. The tokenizer has a token vocabulary. It knows only, let's say, 50,000 or 100,000 tokens. And with these tokens, there are associated embeddings for all of them. This is the embeddings matrix that is part of the model. So if your tokenizer knows 50,000 tokens, your embeddings matrix has 50,000 elements to use for that translation. And at the very end of that process, the model scores all of the tokens. It assigns probabilities to all of the 50,000 tokens. And then from that token probability, you can choose either the top one, or you can have more clever ways of decoding. And these are the various decoding strategies that occur. In practice, there are two steps in generating with GPT models. This is the first step. So the first step, you process all of the text, and this is called a pre-fill step. So all of the tokens are processed here. So that is what generates. You can think of them as being processed in individual tracks, and the final track is what outputs the next token that's going to come afterwards. In the second step, what we learned since, let's say, GPT-2 is that you can cache all of these, so you don't need to redo the processing, and so that's how the next tokens sort of keep getting faster. You can zoom in then and then look at the embeddings, the vectors that sort of flow through these models, and each layer does a little bit of computing and then passes the vector to the next one, and that's how that process sort of ends up happening. The transform block itself is made up of two major components: the self-attention layer, which is where the paper gets its name. Attention is all you need. This is what they're talking about, the self-attention mechanism. And then a feed-forward neural network. If you only had a model with feed-forward neural network, it can do some tasks. It can do some tasks like this. So if you give it the text, the Shawshank, it can predict that the next word is redemption, in reference to the film, because the Shawshank is not a very common word, so statistically it's able to sort of make these inferences. And it does that. It's a dense model, and that's an architectural detail that you often see. And I'm planning to go today and tomorrow into the GPT open source that just got released yesterday and sort of verify, are they still doing, let's say, 4x the size of the internal hidden layer or not. But these tended to be sort of how a lot of these models are structured. And then attention helps the model make sense of the context. So when the model is processing the word it in an example like this, where it's the dog chased the llama because the model needs to understand, does it refer to the llama or to the dog? And attention helps it make sense of this. It helps it bake the right information into the representation of the token it, so it's able to make the process. You can think of self-attention as this method of processing tokens, where if you're processing the last token in red, this mechanism allows you to bake in information from previous ones that are relevant for you to process this current one. And you get all of the positional, let's say, vectors in the beginning, and then you have a vector that is enriched with the contextual information at the very end. And it's broken down into these two steps. So the first one is relevance scoring, and then combining information. And if you know that, I'm not going to go into the details of keys, queries, and values, but there are, let's say, these intuitions of how you make these multiplications. They're kind of straightforward after you understand them. They're a little funky to sort of deal with in the beginning. But you end up with, this is where the first transformer ended up. So you have this attention mechanism happening in parallel in multiple attention heads, and so you have different opportunities to focus on different areas. But one of the first improvements of current day transformers that improve over these 8-year-old transformers is this. So this is multi-query attention. So this is a kind of optimization for the attention step, where instead of each attention head having its own key matrix and query and value, they share the keys and values. You use the same matrix across all the heads, and you only have individual queries for the various attention heads. then it turned out as you scale models like this, the performance goes down. And so this is what a lot of the current models actually do now. This is grouped query attention, where you have groups. So you have maybe 4 attention heads. You can split them down into 2 groups, and each group sort of shares the key matrix and the value matrix, and then the attention heads sort of split. So if you've bared with me so far, that's great, because now you can look at papers that describe the architecture of these models, and then you have now an intuition for each of these. So this is the, let's say, Llama 3 paper. So when you see layers, those are the transformer blocks. Now we know when it says it has 32 layers, it has 32 transformer blocks. When it says the model dimension, that's the length of these vectors that flow through, and the embedding vectors as well. When you see the feed-forward dimension, that's the hidden neural network layer. That's the size of that layer. When you see attention heads, that's how many attention heads, let's say, that we discussed here. When you see key value heads, that's the groups. So I think you can look at even models that are generally, let's say, released this week or last week. The architecture, generally, these are the latest ideas or concepts that you need to be able to sort of just get a sense for all of these. And then you have the sense for vocabulary size, and then positional embeddings is also one of the latest, let's say, changes or improvements in these models. And it grew out of this need here. So this is what the original transformer looked like. You have your embeddings, but then you add in positional information at the top, so the model is able to know which token came before the next one. But that was challenging because when you're doing the training, you needed to do padding. And when you naively pad your training data, maybe you have a set context size that you need to train the model in. So let's say 8,000 context is what you're training on. And let's say you have a document which is a tweet, and that tweet does not fill that entire context. So you needed a way to be more efficient with this. And so this is what training packing that happens in the base training does. So where you pack multiple documents, so you have the least amount of padding, and you get the most out of, let's say, the most performance and efficiency out of the models in the training step. But then once you're doing that, you needed to give better signals for the positional encoding for, let's say, this is token 1 in document 2, or this is position 2 in document 2. And that's where we got these rotary embeddings. And up until OpenAI's model that came out this week, that model uses rotary embeddings. Here now you start to see also this shift. So the positional information is now not added at the beginning of the transformer, it's added at the attention layer using a method like rope or rotary embeddings. And so this is where we started. This is the figure maybe you've seen in the past. Now you know what a language modeling head looks like. You know what a transformer decoder block looks like. The encoder is very similar. So this is where we ended up on the right. This is where we started on the left. They look very similar. Some things have switched around, just where you do the normalization. For attention, now you're doing grouped query attention. You're doing rotary embeddings. You don't have positional encodings. Otherwise, the transformer stood this test of time. There's only like 5, 6, 7 changes. But as we saw in the beginning, the training data and the quality of the models that are able to generate it, that's where we got a lot of the uplift in the previous years. The common standard model right now is a mixture of experts model. And so that's another concept that sort of is great to have a sense of. And experts, my co-author has maybe the best guide of this, a visual guide to a mixture of experts, and that's, you can name experts like this. So the name is unfortunate because it makes you think that you have a model that is an expert in physics and one that is expert in another capacity, but that's not what it is. An expert in this sense is a sub-neural network. And that happens in each layer in your feed-forward neural network. And you have a router in the beginning of each layer that says, okay, for this token, this is better processed by expert 1. And then you go to the layer 2. And then the router of layer 2 says, oh, okay, for this token, my best expert to make this process or do this processing is expert number 3. And that's how you, and the models can sort of shift. Each layer has its own router. This is how we can think of the routers. They're sub-neural networks, so not all, the majority of the parameters don't need to be activated in the forward loop. So you can have a lot more representational power, but when you're doing the forward pass through the model, you're activating a much, much smaller number of neurons. The DeepSeek R1 is no different, but the first three are traditional, dense transformer blocks, but then everything after 3 is a mixture of expert model, and the processing goes sort of one by one like that. The major architectural shift there is that it's not just one expert that is activated, it's 8, and then you have a shared expert that is always sort of activated. So whenever, let's say, an input token comes to block number 4, this shared expert on the left is going to process it, and then 8 of these 256 experts are also going to process it, and then there's a way to sort of merge them and synthesize them, and that's what gets passed to the next one. And that's what we did. That's what happened the last 7 years. That's how this jump from T5 to Manus and today's agents are able to happen within just the span of 5 years. It started out kind of like this. You have text in, text out. You can solve easier problems, but then now coding problems are measured with SWE bench, software engineering benchmark, where the input is a GitHub issue. You're saying, here's a link to a GitHub issue, go solve that for me. And that's what the models now are sort of being rated on in terms of code performance. And a certain solution to one of these tends to be 40, 50 steps, where the model needs to check out, it needs to have access to a virtual machine. It will check it out, it will create conda, it will resolve conda issues, it will replicate the issue, it will find out how to solve it, run the unit tests, maybe write new unit tests to ensure that it's correct. And that's where we are today. Thank you very much. And a reminder about the book signing happening right after.
Okay, thanks. This was a great overview. So one question, right? So how would you comment now these recent developments on activation vectors and looking into the LLM, how the queries are structured, and somehow there seem to be some, we are getting bit by bit, right, towards a little bit understanding on what's happening inside, right? First was this big black box, then it was a little bit smaller black box. Now it seems like there are points of lights somewhere inside, something like this. Could you comment on how you see this maybe next steps, right?
Yes, so a lot of the process, like we know exactly how it's trained, we know exactly how it's structured, but then there's still a major black box into how the actual mechanisms click together. What are the various circuits that it's sort of building? And so there's a bit of research on interpretability of these models, including attempts to maybe map. And some of the most interesting work I find here is ways where you can causally verify. So these are some of the papers on model editing, where you can edit the knowledge of the model and sort of see that manifest in its behavior. And so these are some of the interests, but I do think that we need a lot more work to sort of understand them and reflect on.
But you see promise in this direction?
Oh yeah, for sure, for sure. Yeah.
Thank you for the great talk. Just a high-level question. Do you see a trend or shift anytime soon away from the transformer architectures like state space models or others that can, like, any innovation happening at the model layer?
So I will have to also plug my co-author Martin's blog post on Mamba and state space models. They're still not there yet. They're not competing with transformers at these scales yet. The transformer is still sort of king in those areas. I'm excited to explore more of diffusion, text diffusion specifically. So diffusion has done wonders in video and audio and images. So I'm really excited to sort of dig deeper into text diffusion. It makes sense. It's super fast. So that's where I'll sort of look next. It'll probably share a lot of the same ideas, but there's very little challengers to the transformer so far.
Thanks, Jay, for the great talk. I have a question about the evals. So we all know, yes, we are moving towards the very fast speed for developing more models and more complex models and with agents. How do you feel about the development on the evaluation side or measurement for these black boxes and more complex systems that we are building?
Yeah, evaluation is one of these, it's probably one of the most important areas. I think for adopters and users of these models, they need, knowing how to evaluate the model is probably the first skill that they need to, even if they're not training a model, even if they're just choosing between vendors, if they're not able to have their own test set that to sort of pick the right vendor, they're not going to be able to. So I look back a lot on, let's say, good software engineering practices of unit testing and regression testing and saying LLMs need to have exactly that. So if the next version of the LLM regresses on some of your, let's say, behaviors that you require out of it, you need a part of your system that captures that. And so evaluation is still broken. People sort of try to hill climb and sort of compete on either academic or everything that gets, whenever anything becomes a goal, it becomes a broken metric to compare sort of models. And so we definitely need a lot more work as an industry and as individuals, and even the final adopters, they need to sort of at least create a small unit test set for your own task, your own final task, that a lot of the times will not correlate with AME 2014 for reasoning or with MMLU or something else.
Okay, thanks.
Who goes before me sounds waiting. Thank you for the talk. That was really great. I had a question on model merging. I thought that was really interesting and something I'd like to try. But I was just curious. So you give the example of model 1 good at coding and model 2 good at drag, and then we average the weights of two models out. Does that make the model less better than what it was before? So it can become good at both tasks, but maybe not as good as an individual coding model? Does that make sense?
Yeah, the code expert would end up being better at coding than the merged model. But then you elevate both capabilities using this, and you can get very close to the performance of the original expert.
Okay. So it would be more useful when you want a model to be able to do both at a good enough.
Yes, yes, because a lot of these models are expected to solve a wide variety of problem types. And a lot of the times you want different teams to experiment with different kinds of data mixes, with different training styles and parameters to actually get that capability working. And then this is one tool in the toolbox. It doesn't have to be that every model that you train uses model merging, but it's just one tool in the toolbox for these scenarios.
Thank you.
Thank you.
Thank you, Jay, for a fascinating talk. I really liked it. I have a question regarding the mixture of experts. So obviously we are trading some trading efficiency for inference time efficiency with mixture of experts. What do you see the trend here? As in, like, until Llama 3, it was like densely trained transformer architecture. With Llama 4, we have mixture of experts. And again, I think the reasoning has been that it was very hard to get the mixture of experts right in the training phase. Do you really see that like mixture of experts being the dominant architecture going forward, and do you see like it being a really good alternative to maybe even model merging that you're doing at Cohere?
So it's becoming more and more common, where in the beginning it was you tended to mostly see dense models, but it's still painful. Like large, even if you're not activating all the parameters in your forward pass, they still have to be loaded on your GPU. They're not sitting on disk. So the big model is let's say still painful to deploy if you're going to go with a DeepSeek. R1 is 600 billion parameters, and even commercial deployers of it don't even have enough sort of capacity. And so one way around that is to say, okay, create the teacher model, which is it can be a sparse mixture of expert model, and then you can extract or distill dense models that can fit on a phone or can fit on a laptop or can fit on a use case. So that's one way, but we still need more and more efficient models. But it was clear that being mixture of experts gave it a lot more representational capacity to train on more data and improve performance across those data sets.
Okay. Thank you, Jay. Great talk here. So today, we had two keynote speakers, and they mentioned about and we might still need to trust the human intelligence more than the machine learning or large language models. And one like the Carly mentioned about the causality, and Jason mentioned about the way how the human intelligence could still be better in many different steps when he's trying to design the chips here. So my question back to you here is, since you have been exposed to the state of art in this area, and given the human intelligence you have, and now when you see the transformer, which was developed 7-8 years ago, how do you see something you're understanding about why transformer is working previously, and why is transformer working now? Do you see any bigger insight you have gained so far, given all those progresses or maybe research directions has been expanded from the paper?
So, are you asking sort of a trust question in terms of deployment, which use cases the current transformers are able to do that ones from 5 years ago were not sort of able to do?
No. Maybe I didn't really rephrase my question very well here. So my question here is 7-8 years ago, we have our human intelligence have our initial understanding about why transformer will be working.
Yes.
Now, the transformer has been used in all different areas for almost 7-8 years. I'm pretty sure humans understand the transformer way better than 7 years ago. So if I ask you, if you could summarize one of the key difference in your current understanding from your understanding 7 years ago, would you be able to mention a few points which probably we didn't understand at that time, but now we have a better understanding now, and which can maybe guide some of the direction in the future, so maybe a better framework we can be happy.
Yeah. Okay, so we still have a lot more to learn, honestly. It's the answers that we have currently for why these capabilities sort of emerge are not yet sort of extremely satisfying, but it's empirical in terms of it works. And when we train it with enough data and we measure sort of the benchmarks, it gets better and better at those use cases. But that goes back to, let's say, maybe interpretability, to get a lot more of the insights of what structures emerge in these, let's say, neuronal pathways, if you want to call them that, that actually enable each of these use cases. I think we still have a lot of learning to do and exploration to do to sort of get a better understanding of all of this.
Okay, thank you.
Hi, my question was mainly on in your opinion, what do you think are most important in preparing the pre-training data corpus in order to produce a high quality large language model?
Yeah, so pre-training has to have very high quality, and the more tokens you have, the better. And multilinguality now is a major part of it as well. So you have all the languages that you want the model to be good at. And even the developments in reinforcement learning, people are seeing that you're only getting a high quality reinforcement learning model because you had a very high quality base model. And so the more, and you're starting to see the data that was generated for the reinforcement learning step being sort of injected at the base training step. And the DeepSeek-R1 paper had this aha moment where it's a step in the training process of the model where the model was starting to sort of doubt its answers and say, let me look at this problem in a different way. And then that sort of improved. And so people were saying the aha moment comes from RL alone. And then there were other papers that came after that and said, no, there are aha moments in the base model as well. So that capability was there in an unpolished sort of format in base training. And so, yes, base training data continue to need to be better and better. And data that's generated for, let's say, downstream applications for it need to be brought back. And then more data needs to be in distribution. Now you're seeing, I don't know if anybody's used Claude Code, for example. Now you have these very long horizon problems. So I showed you, let's say, a coding problem with 50 steps. If you're building an application, you can have 30 of these 50-step problems. And so now you're talking about problems of hundreds or thousands of steps. So the more you can sort of pull that structure of data and you show it to the model earlier and earlier in the training process, you're sort of going to get better and better agentic models.
Thank you.
I have a question about RL training, RL fine-tuning with tool calling, especially for things like deep research agents, which, like you mentioned, are very long horizon, really long trajectories. I guess there's two questions there. One, there is a verifiable reward at the end of a deep research report, so how do you construct the reward? And then the second question being, when you do have this long trajectory, how do you credit assign to different tool calls you made along the way? How do you think OpenAI does it? Do you use some proxy rewards? Curious for your thoughts.
Can you repeat the second one? Sorry.
How do you credit assign specific tool calls when you have a long trajectory and then a final artifact at the end, like a deep research report?
Okay. Yeah, I think the algorithms like GRPO assign, let's say, a score for the entire sequence. And that assigns, let's say, the token. So a lot of that is delegated to just the RL algorithm that you're using, and they tend to be sort of similar. So we use one called RLOO. These are the reinforced style. These are also group models, group methods like GRPO. And that's a little bit. There was some. Before R1 came out, there were people who were dealing with process reward models where you can evaluate, okay, these are the first 5 steps in the process. How am I doing so far? Give me a reward. This is a reward model that enables you to not evaluate just the final result, but each part of the step. And that went out of favor because people were saying if you just assign the reward value at the final result, that tends to improve the entire flow in each of the individual steps that happen before it.
And the first question was about for things like deep research where there's no verifiable reward, what are the rewards?
Yes, that is a great question. You'll probably need synthetic data. You'll probably need some annotated data as well. But that is that's one of the most, probably one of the first agents that truly captures the world's imagination. So RAG and advanced RAG and then deep research. And they're not, I don't see a lot of recipes out there for it, but it will have to be things like, you label as many of them as possible. You can do variations of them with synthetic methods. And then can you do an entirely different, let's say, can you do a synthetic rollout and then have humans rate them, for example? And do that. But these are the tools in your toolbox. Now you have very capable models and you have human annotation, which is expensive. And you use a little bit of both.
Thank you.
Thanks. My question is about long context inputs. I think with some of the problems like the ones you identified where you need to solve 50 different problems, or with multi-agent frameworks, the input context can become very long. I'm curious to hear your thoughts about if there's been any big breakthroughs in extending the context window or maybe techniques for working with a limited context size context window? Just, yeah, curious to hear kind of your thoughts.
Yeah, that's a great question. So right now we have models of 1 million and above context size, and the more of these that come out, the more we have use for we invent problems that need even more context, so they will continue to sort of come up. Long context in the training process is introduced gradually, maybe towards sort of the end of the base training, where most of your training happens at a smaller context size, say 32,000 or 8,000, and then sort of a lot of these post-training recipes grow the training around the end of the training. They say, okay, let me show the model longer and longer sequences now, because that helps you sort of preserve on compute. So that's a little bit of where it happens if you're creating the model yourself. If you're the prompt engineer at the level on top of it, there are things like, if it's the model, you need to track how many tokens you have in the context. If they reach a specific level, maybe you summarize them and provide a summary, and then that's what is passed to the next step. The agent I showed is from this company, Manus, M-A-N-U-S, and they have an incredible blog post about all of the tricks that they sort of use. Because they say in the beginning of the company we made this choice that we're not a model training company, we're a prompt engineering company. And they got very, very far with it.
Thank you.